get Leila, do you want to do the introductions?
Sure. Welcome everyone. And today Tarun is our presenter for the Dual Information Bottleneck, and the floor is all yours.
Thank you, Leila. So yeah, so we had
Tarun,
seen,
you have to switch screens. We are seeing your presentation
okay.
on screen. Swap displays. There you go.
Beautiful. You're back to the first one now.
Yeah, is it good?
Yep.
Now it's perfect.
Yeah, so last time Professor Hoshin Gupta was talking about the information bottleneck. Now we are going forward with another paper, like the extension of information bottleneck to dual information bottleneck. So let's recap the information bottleneck first so that we can understand how it extend this idea or the concept of IB to dual IB. So our target is to predict Y in all the machine learning theories and in general with the information in X. So if you see this diagram here at the right bottom, this is like an encoding decoder problem, right? So we have some images, some input data at the starting, and we compress it through the multiple layers, hidden layers and other layers in the machine learning. And then we compress it to the relevant features that we have, and then we decode it to reconstruct the images back. So this is the method we use generally, even to share images or share any data through internet or through other media. We generally send it to them. So in between what media does, it compresses, it captures the relevant information, and then our computer again decodes it, and we see the full picture again. That is the idea behind. But bottleneck comes how how much we can compress this information, and can we capture all the relevant information in between? Because if we don't have the relevant information, we'll not be able to construct the image back, or the data, whatever we are getting, will not be able to decode it back to its original form. So this is the information bottleneck actually. So even if we take an example in the sound waves, so entropy, so we are talking about in terms of information theory, and this is like encoding in the machine learning process where all the nodes will be connected together and then they connect to the specific feature and then decode. But also we can connect it to the information theory part where information is propagating from one hidden layer to another hidden layer to another hidden layer. It forms a Markov chain because every layer will compute itself after its prior layers are computed enough, and then it will compute the current layer, and then it will compute the next layer. So why are we saying that information relevant, like we have some input data and we are trying to compress it, like why it will compress it? So that is the biggest question, right? So if we take an example of sound wave, that overall information buried will be like all the transcript and all the noises and everything. But actual transcript, if somebody writes it down, it will be much lower entropy. Entropy means it will have much lower information, which we want to extract. That is the relevant information that we want to capture from the original data set. So it compresses the data as well as it will not lose the relevant information, and we will get all the information that we need. That is the overall idea behind this approach. Okay. Yeah, so this is the bottleneck where we have input data and we have output that we want to get, and we are compressing with the X tilde. It can be lossy compression, it can be non-lossy compression. So we are trying to compress or encode this information. This is all information bottleneck. We are trying to compress and encode all the information, relevant information in X to the X tilde. And then we will, depending on the probability distribution between X and Y. X is like input and Y is the output function. So compression can be thought of as a minimum description length, which is also can be seen as a mutual information between these two variables, like the compressed representation and the actual input data. For the example, the sound wave has entropy which is much higher than the entropy which the transcript has, which is buried into the sound wave. That is the idea behind. So can we compress, and how much can we compress, and is there a bottleneck? Is there a upper limit or down upper limit to the compression that we are trying to see? That is the thing. So if we see in this diagram, so entire concept is down on the thing that we have a distribution about the output and the input, the probability distribution, and we are trying to get how much we can compress. So this optimization of compression will be seen as again a maximum. The X tilde captures the maximum information about Y being a reduced order representation, and compression will not have more information about the Y than the original data. This is like very obvious thing, because we are compressing, and it can be lossy compression, it can be non-lossy compression, but generally if we are compressing something, it will lose some kind of information, and we are trying to see like how much we can get out of it. So information between the compressed generalization with respect to Y will be less than equal to the information that we have from input data with respect to Y, like for the input output mutual information. So equality will hold when we have non-lossy compression. So to optimize this problem, we can write it down in terms of distortion rate. So here is the mutual information between compressed representation and the input data. And this D here is the expectation of the distortion rate, and this beta parameter controls how much rate that this parameter will have, how much information is passing through. It's like a bottleneck kind of thing, where we can control how much information from the input data is transferring through that X tilde, and we can like how much we can decode to Y. So if you see in this diagram at the down, the topmost is lowest distortion. We will get so this X tilde, this portion will be 0. And then we will have all the mutual information between. So this will be like very high, and then distortion will be very less, and we will get output which is like equivalent to the original data has about the output Y. And if we go down the line, if distortion is too high, then we will not get like all the data will be lost in between in the process, and will not get the output as we want to get. So beta 0 is high compression, and info rate will be low, but beta infinity is, if beta is very high, then the compression will be very low, and all the information is passing from X to Y without being captured or without being compressed into the X tilde. And we can solve this optimization problem using this BA algorithm, Ballahu-Taramoto. We can write this optimization, this distortion function, as exponential function of that KL divergence between the distribution of Y given X and Y given the compressed representation. And with the iterative process, we can get the distribution of X tilde, and we will get the compressed representation, whatever we want to get, like how much we can, like what is the upper bound of the information that we can have from that. And we can also write this equation into this. If we open it, like simplify it, it will also be, it can become as a mutual information between the compressed representation and the input data, as well as the whatever we get from the compressed representation as the output. So we can also optimize this equation. So optimizing this will mean that we are decreasing the mutual information between compressed representation and the input data. That means we are compressing the information and extracting the relevant information, and we are increasing this information, which means that we have all the relevant information buried into the compressed representation, which is there in the X tilde. So what are the limitations of information bottleneck? It doesn't preserve the structure of distribution. It completely depend on the decoder-encoder probability distribution, as we have seen. So it depends on the probability distribution of output distribution with respect to input and with respect to the X tilde. So it doesn't preserve the structure. And then it is also completely non-parametric, operate directly on the encoder decoder. Again, it's a same thing that what is the limitation of information bottleneck? If you see in this figure, if you have enough input data, it captures all the relevant information or all the patterns buried into the input signals, and it compresses the thing, and then it will decode to an output signal. But what if we have very limited data set? Then it will increase, like it will compress the data set, and to an extent, then it will go down, which means that it is over compressing the thing. And like the generalization and memorization, all the machine learning things, there are multiple studies which shows that it is not the overfitting that it's not always overfitting, but the machine learning, how it learns, first it will understand all the patterns, and then all the patterns are done, then it will go for the noisy, all the noises to
Tarun, can you hear us?
I can hear Leela, but I can't hear Tarun.
Yeah.
I think he froze.
Okay. Where is he calling in from, his house?
I don't know.
I'm gonna contact him by cell phone to see.
Okay. He's in Illinois though, right?
Yes.
Maybe
We
his
never
internet
know.
went down.
We never know. No, he said he'd meet me today afternoon, so I think he's here.
At least virtually. Did you see that article about the foundational models that all these big companies are building?
No, which one?
I thought I sent it to you yesterday.
Oh.
If I haven't, I'll send
Yeah,
it.
I was in a flight though. Most of the
Okay.
day I'm flying back from California yesterday. So.
They're talking about the fact that they're building, giving huger and huger, building, models now that have billions of parameters using transformer networks like BERT.
Yeah.
And they're feeding them more and more and more and more data. And how, as they keep increasing the size of the models, their capacity and their ability keeps increasing, so that they're becoming general purpose networks, because they're learning from the entire corpus corpora of internet data and information, and then they can answer questions in a seemingly intelligent manner.
Okay, so this is the Economist article.
Did I send it to you?
Yeah, I had started
reading
it, but I couldn't finish.
But the interesting way they work is that they're self-supervised. So what they do is they randomly leave out words or sentences or phrases or ideas, and then they learn to predict what those things that they left out are. So they have the full data set, right? And they leave things out, and then they predict them, and then they compare against what they leave out, and that's how they train their parameters. So essentially, it's like a Bayesian learning, and it makes a lot of sense because it's kind of similar to the way we process information about the world, right? Or it feels to me similar.
Yeah, reminds me of those diagrams where you put a little thing at the top in the corner, and then we fill in as a triangle, right? Our mind goes in as a triangle.
But human beings are constantly correlating all of our sensory information, right? So they don't have sensory information, but they have the whole corpus of conversations that are happening on the internet.
Yeah, let me share the screen again.
Hi, Tarun. Did your internet go down?
Yeah, I don't know why my internet went down. Can you see the screen presenter mode?
Yes. The
This is
last
the
thing we
presenter.
heard, the last thing we heard from you was that the thing was compressing, and then you started to talk about fitting the noise. Yeah.
I think it happened again. Tarun, can you hear us?
Again, Kala, are you saying?
Yeah, I think your video is frozen, but we can hear you.
Yeah, your screen is
Okay.
Tarun.
So
Why don't you turn your
still it
video
is
off? Just turn your video off.
actually, let me do
You won't
one
be able to share the
thing.
screen then.
Yeah,
You should be able to
that's
share
right.
the screen.
But I can share this presentation to Lala, and then probably she can show, and I can join through phone.
Yes, let's do that.
If that will work, right? That will be much better.
Yeah, or you can stay and just close the audio and close the video and speak.
Yes, sure.
We should
Let
still
me-
be able to see your screen if you turn your video off.
Is it?
Right now, we're not seeing anything.
Oh yeah, just a second. It doesn't like it is happening for the first time. It didn't happen before.
Just as it was getting very interesting, Tarun.
I don't know
It's
if
a 2
Tarun,
MB file. I think I'm not able to send it to Lala too.
just put it in
Probably I
Dropbox.
can just
Put it in Dropbox and share the link.
my video and then try to share it.
Tarun, if you can hear me, put it in Dropbox and share.
Yeah, but for that too, I need a internet. It is. I'm not able to share. Let me see. I have shared it with Lara. Yeah. Lara, did you get the email?
No, yet, Tarun. I am refreshing the email.
Just put the link in the chat, Tarun.
Yeah, if you can put it in Dropbox and share the link with me in the chat, I can project.
Okay.
Yeah, because it's not getting into my email. No chat.
So, how do you share a link to a Dropbox?
if you go to your Dropbox, you will see 3 points, vertical points, and then from there, if you click there, you can, there is an option that says share link.
Mhm.
And, I think you can copy the link from there and put it here in the chat.
Can I share the entire PPT to this?
I got your email. Okay.
You got my email?
Yes. Give me a second,
Okay.
and I will try to download it.
Yeah.
Yeah, I got it. So
Yes, thank you.
sure.
Yes.
Can you see the screen?
Yeah. Thanks a lot.
You tell me next whenever it is.
Yeah, I
your
will tell
time
you
to
the
continue.
next. Can you, yeah, can you go to, yes. Okay. Yeah, so I was reading a review of this, why this happens. This happens means like you cannot see my pointer now, but the compression that you can see in the left-hand side figure, like after this green dot, it is going down. So it happens with the less, and if you have a less data in the input, then you cannot like there is a limit to encode it and then decode it to the output variable. But what if you train it to a very large number of epochs, like here, so it is going towards 10 to the power 4 epochs. If you train it too much, then it first recognizes all the patterns, and then it will overfit based on the noise. So noise means all the extra data that it has, it will try to overfit using that. So it does very good with the training data set, but not very good with the testing data set. That happens because it overfitted in the training data set. That's why we are seeing this kind of compression, even with the mutual information between the compressed representation and the output is also decreasing because of that. So this is the limitation of IB that they wanted to overcome. Yeah.
Tarun, what's the difference between the left figure and the right figure? One is training and one is testing, or?
No, so this one is like for the different data sets. So the left figure shows very less, like 5% data set we are using for the testing. And then for the right figure, we are using 85% of the input data set as like training.
Okay.
So if we have, yeah.
Just so I can make sure I interpret this correctly. So if I'm looking at the right figure or the left figure, and I start at the bottom left-hand corner, first I'm learning the patterns in the input data. So that's why the mutual information is increasing.
Yes.
Between X and T. T is the compressed version.
Mm-hmm.
And then on the right one, at the same time, I'm improving my ability to predict Y. And on the right one, my ability to predict Y keeps increasing, but my mutual information between X and the compressed version goes down. Whereas on the left one, both of them go down. So the model is actually getting worse. Okay.
Yes. Yeah, that's the thing. And this happens if you see an example of image recognition. So if you want to capture an image of dog, it has a brightness as an extra information, which is not relevant. And the sky and other things like roads, grass, or anything, XYZ can be possible in the image, which are not relevant for our output as Y will be the dog, for example, right? So if we give very less of those training data set, like input images are very less for that. So it will try to capture sky and then other irrelevant information and try to overfit in the dog's image. So that kind of thing happens if we have very less input data set versus if we have a very large input data set, because then we have all the like variation, unseen patterns and everything buried into all the input images. And then we are getting a good compressed results, which is like encoding to all the relevant features and then decoding to the actual image that we want to get. So that is the limitation of IB, and they wanted to overcome this limitation. What if we have very less amount of data set? Can we still predict the better thing? So if you see on the top hand side, they added one more variable, which is like y tilde. So they say it's like a Markov chain. If you have y and x, y is the output field and then x is input. If you have these two things, then you will like the first part, training phases with the IB. What is the prediction phases? What we are getting with the unseen parameter. So y tilde is exactly y, but with a different distribution. So we are testing it, how much we are getting, like how much structural representation we are getting from the compressed representation that we did in the X tilde. That is the thing that we are doing. This is the only thing that they added in the dual information bottleneck to get, and there were many interesting properties also they were coming through this addition of y tilde, which we will talk about it. So it breaks this assumption of the complete distribution knowledge about the distribution which the information bottleneck has. So it was all completely dependent on the probability distribution between X and Y, the output and input data. So now we are using this y tilde to get how much we can preserve the parametric structure, which is there in the input data and the compressed version X tilde. And if you see, it doesn't change the overall structure of the encoder and decoder. So even if we use the y tilde, it will, for the large sample space, the probability distribution between y tilde given x and the probability distribution between y given x tilde will be exactly same. So for the higher beta with the lower distortion, it will behave the same and it will give all the information through all those two bottlenecks. So that is the dual information bottleneck. Can you go next? Yeah, so they changed the distortion function in this, which is now dependent on the y tilde. If you see the first and the second equation, distortion function is given by this KL divergence, because we are playing with the information theory part and how this information is propagating through one layer to another layer and how much we are capturing at the lowest node, the compressed representation, most compressed representation, how much we can decode from there. So it depends on the y tilde portion, and if we simplify it, it simplifies to very similar structure as the information bottleneck. We are getting a mutual information between x tilde and y tilde, how much like compressed representation plus how much parametric the structural component is preserved in that. We want to like minimize that, and then how much we are getting from the input data. And then there will be an extra B term, which is like a positive term of compressed of this KL divergence, like how much we are differ, how our that second bottleneck is differ from the actual representation that we want to get. So that is our distortion function, like extra term, which we are still getting from there.
So
and
they
both of
they're minimizing to obtain what?
To obtain this, so finally we want to capture the distribution of x tilde and y tilde. That is our major aim, or x tilde, if you want to simplify it, so that we know how much information, like how much we can compress a certain input data to get an output, certain kind of output.
Okay.
Yeah, so structurally and everything is completely same. It just captures it just preserves the structure and the distribution of the input data and the features like the parametric structure which is associated with the relevant features that are there in the input data. It preserves that. And both term vanishes when x is equal to like is the sufficient statistic, minimal sufficient statistics. If these two are equivalent, then both the terms will vanish and it will be same as the information bottleneck. So
I have a
it means
question.
that
I
we
have a,
are.
I have a question there, Tarun. Do you really mean when x equals x tilde or when I x tilde is equal to 1?
Say it again, Hoshin.
When x is equal to x tilde, then x tilde is just the original input data. Is that what you mean, or do you mean when x tilde is a sufficient statistic of x, meaning that I of x tilde is equal to 1?
Yes, actually, yes, the latter part. So it is sufficiently statistic, like
Okay.
our beta is high, and then all the information, relevant information, is passing through that bottleneck. So
Okay.
it will behave like a normal information bottleneck.
Okay.
So that also means if we can relate it with the larger data set versus very finite set of input data. So if we have larger data, we have all the patterns, which are, it will be there in the input data, and there will be no unseen patterns to like to predict the y. So it will, both of them will behave same in that condition if you have larger data set than the lower, like the finite data set. It will not be, for the finite data set, this distortion function will not behave as same way as information bottleneck distortion function behaves. So it is kind of preserving the structure which is there in the relevant information, like as x tilde.
So would it be fair to say it's kind of imposing a kind of a regularization?
Yes, yeah, kind of.
Okay.
Yeah. Can you go next? So again, the same thing we did with the information bottleneck. We can solve this equation with the BA algorithm, Ballyhoot Arimoto algorithm with the iterative process. So at T we have something, and then it will change to T plus 1 and T plus 2, and we can have a compressed representation of x tilde. So basic structure of equation, again, it is like I said before, that equation structure of equations of IB and dual IB are the same. So it approaches each other at the large values of beta. So if we have very large beta, that means most of the relevant information is passing through, and then we will, and all the unseen, there will be no unseen patterns which is there in the x tilde, and we are getting a good output. Next.
So sorry. So what's actually different in this set of three equations?
So instead of arithmetic, I think they have changed this third equation to the geometric mean, and they believe that geometric mean will have better prediction power. And in this exponential of the first equation, they are not directly using the distribution of y, but they are also getting a random distribution of y in terms of y tilde. So they are kind of training it for the first part and then testing it for the later part, like how much they can test it, like how much accuracy they can get from the training set.
Okay, I don't see y tilde in the first equation, but probably I have to dig into it. Thank you.
Yeah, so yes. Can you go next? Yes, so again, this figure is, so after this figure, entire thought process of going from information bottleneck to the dual information bottleneck was this figure, why we are getting a compressed thing and what are the properties of information bottleneck and then dual information bottleneck, how they differ and everything. So one important thing which they noticed is if you see these green dots, it goes from very low information, like very compressed. If you so all these lines, the bold lines are the layers, different hidden layers within the system, and the color is showing the number of epochs, right? So till the green dot, it learns very fast and it compresses really good. But after that, it takes a lot of time, like all 80% of the time is to really compress it to very nice features and extracting like all the information, all the relevant features very nicely. So why this is happening, like it is compressing to a certain point very fast and then uh, going to a perfect condition, it takes a lot of time to train. So probably they thought it's a like a critical point in there, and all the training critical point is kind of diverging. That's why it is taking a lot of time to train it to the perfectly extracting all the relevant information. So these are like there are few properties which are different in the dual information bottleneck and the information bottleneck. Can you go next?
Tarun, sorry,
Yeah.
can you go back? Just to be clear, I'm not sure if people got that and if I understood it correctly. So if I look at the figure on the right, I've got these
Mhm.
3 purple lines, heavy lines. Those represent different layers. So the one on the left represents the first layer, the second one is the second layer, and the third is the third layer of a deep network, correct?
Yes.
That's why the later layers have higher mutual information than the earlier layers, because they haven't learned everything that's necessary.
Yes. Yeah.
Okay, thank you.
Yes. Thank you. Thank you, Oshin, for clarifying that. Yes. Yeah. Can you go next? So in this, they are comparing few properties which are there in the like IB, not just general IB and the dual IB. So what they did, they are trying to characterize the nonlinear eigenvectors and eigenvalues to get uh, the critical beta points where it will differ. And they say why it is happening, that it is learning a lot of things like in a very short time period, and then it takes a lot of time after a certain time. So there are some critical beta points which are there. And if you see in the leftmost figure, these are not very different. So the bigger dash line is the information bottleneck, and the dotted line is dual IB. So why these are different? So they took a very small example where there were 5 input uh, figures and 1 output, which was binary. Figure means like the data set. They had 5 different data set of input, and then result was only 1 binary output. So they tested it on the dual IB and the IB, and both of them were doing very fine. And if you see at the higher beta, they were uh, converging on a same point, but with the lower beta points, the dual IB diverges fast and early than the information bottleneck part, because it was capturing some part of a structural problems which are there in the input data set. And if you see the middle figure, it shows why after a certain point, it takes a lot of time to train its model. So this is y-axis shows the number of iterations, and axis is the beta, like the parameters, Lagrangian parameter. So if you go to a beta C, it will, so till beta C, it takes very fast to learn this program, learn to extract the relevant information. And after, if you cross that beta C, it will diverge. And it takes a lot of time again to converge it here. And this blue line is dual IB, which is this figure shows that it is doing very like little better than the information bottleneck. And as we go higher in the beta axis, we see both of these are converging together. That means it is like behaving as the like dual information bottleneck is behaving same as information bottleneck. And if you see this right hand side figure, it again shows that the minimum length will be like there will be information bottleneck and dual information bottleneck will be very close to each other at the beta c, the critical betas that we get from the analytical equations, and both of them behave almost similar. For the good data set, for the finite data set, will dual information bottleneck will be a little higher. So at the lower betas where distortion rate is very high, so dual IB does a good job than the IB equations. Can you go next? Yeah, and so dual IB is introducing one more parameter, one more bottleneck, but it is still captures the parametric distribution, which is there inside the input parameter. So we can define this probability distribution as a function of exponential function of some parameters, which are part of exponential family, and we can solve it again using the same PA algorithm, and we can get all the parameters, analytical parameters, which are there in the natural parameters or analytical parameters, which are there in the input data. So we are not losing any natural pattern which exists in the input data file. Can you go next? Yeah, this is again the similar thing at the information plane. So this in the left side figure, the y-axis is output information with respect to the compressed version, compressed representation, and x-axis is mutual information between the input data and the compressed representation. Here, if you see, we are varying beta from -5 to 5, and the purple line corresponds to the dual IB. So this variational dual IB is again it's a kind of, so we are talking about machine learning now. Until now we were talking about the theoretical framework, how dual information works, but variational dual information, how variational input coder like encoder decoder works. It uses the mean and standard deviation to propagate back all the gradient descent, all the error components. So it is like little robust than the general encoder decoder problem. So it uses some kind of noise model into it to make a better predictions. So they use this variational dual information and the variational information bottleneck to check how those two equations are performing. And they check from -5 to 5 as a beta values. And if you see at higher beta values, these are exactly same as predicted by theory. And it initially, like for the lower beta values, dual information does very like better than the information bottleneck. And also the middle figure is information, which is their mutual information between input and the compressed version with the steps. So if you see, our problem was for the information bottleneck, it is overfitting the data. Hence, it was like reducing all the information and compressing it to like further compressing even the mutual information which is there in the compressed version and the input data. So if you see in the dual information bottleneck, for the lower beta value, it kind of stagnates, and for the higher beta values it goes to low side, but again it increases. So which means we are not going into the regime of overfitting, but we are capturing all the like the structural possibilities from the data. And accuracy wise also we can see the dual information bottleneck is better than the VIB. So this is all that they talk about in their paper. So next, yeah. So if you have any question, so they just in the end I wanted to say just they added one more term to to get the better prediction and to preserve the structural distribution which is there in the input data. But I also read their reviews, and they said it's like a KL divergence in the reverse order, and they were not very sure that it is like a very theoretical model and haven't tested before. So the reviewers were like kind of skeptical about whether this will work or not in the actual scenarios, or how it will work. Will it be different from the original theoretical framework that they are presenting? So they did few examples, like very small examples, but how it will behave in the real data, they were not sure. So that was the major review portion. Yes, thank you. If you have any question, we can discuss about it.
So Tarun, could you say a little bit more about this breakpoints where the training speed decreases? I'm not sure I quite followed what you said was their rationale for why the rate of learning decreases after some thresholds.
Yeah, so one possibility can be that the machine learning algorithm or the theoretical framework, it learns the basic structure of input data, and then it will go to the next. So it learns in a batches. It doesn't learn everything in a single row. So how I understood it, it learns the basic, the very obvious parameters and the obvious structure of the data, and then it learns the other nuances, and then it goes, if everything is learned, and then it will go to the noise and see if it can overfit the data point.
Okay.
So because of that, these critical beta points are coming.
Just speculating out loud, but in human learning, there's this idea that we tend to learn very quickly, and then we have a threshold and it takes a long time, and then suddenly we learn again and we hit a new threshold. The example often used is learning how to play tennis. That, in the beginning you just get good at hitting the ball over the net, but then it takes a long time before you can hit it more accurately, and so on. I was just intrigued by that analogy there.
So something that's not clear to me, I'm trying to put my arms around, is how does it connect to the neural network? I mean, because the training of the neural network has its own framework. Are they changing that to incorporate these ideas of information bottleneck?
I believe they're changing the cost function used for training the network.
I see. Okay. So the
But I
cost
could be wrong, Tarun. Is that
Yeah,
correct, Tarun?
Yeah, it's correct. Yeah, so they are using the conditional entropy and all the information bottleneck equations into the cost function of machine learning paradigm to train this thing.
So one of the critiques of the earlier papers, again, Praveen, was the issue of whether for large networks you can actually measure the mutual information accurately enough. Did they talk about that again, Tarun?
Say it again, question.
In the early information bottleneck papers, when they applied it to machine learning, they got a lot of pushback and there was a lot of critique. And my reading of the critique was that one of the major issues was how well or how accurately you can actually measure mutual information, given the amount of data that you have, and whether you can do that in the high dimensional spaces. Did they address that issue again in these papers or no?
No, they didn't address. Actually, this was also a critique from the review, and they said it's like completely theoretical framework. And
Mm-hmm.
like you also suggested last time that even with the binning and mutual
Mm-hmm.
information can change through the binning, and which
Mm.
which method do you use to calculate the mutual information? And it will also change the actual figure, why it is compressing and why it is learning so fast and so forth and other things.
Okay.
So they didn't answer those questions.
So the theory is interesting, but the practical implementation is still requires some development of tools, it sounds like.
Yeah.
Can I ask you to go back to the first slide of the dual information concept? No, you just passed it. I'm still a little confused as to what you mean by y tilde. When you say y tilde is same as y but distributed differently, I don't quite understand what that means.
So so I think if we have, so information bottleneck was completely dependent on the joint probability distribution between output and input.
Correct.
So there we believe that
Meaning
all the
meaning it assumed that you knew what the distribution of x and y was, the joint distribution
yes,
for the
yeah.
theory.
So
Yeah.
I understood this. If it is distributed randomly or differently, then it will capture the unseen parameters too. Otherwise, it will not get
Sorry.
those unseen parameters.
Sorry. What do you mean by unseen parameters?
Uh, Unseen patterns, not parameters. Sorry, unseen patterns. So in
What do you mean by
IB,
what do you mean by
so in
unseen patterns? Yeah.
yeah. So if we have enough information, like enough input data, then it will learn perfectly, right? But if we have finite data set,
So
then
by unseen patterns, you mean patterns that are in the distribution but not in the data?
yes.
Okay. Sorry, keep going. Yeah.
Yeah, so for that, they introduces this y tilde, which are like same as, because we don't have the actual actual output, what that will be, but they are trying to redistribute it and trying to see if something happens differently,
So
then how it will behave.
y tilde is predicted by the model.
Y tilde is, it's the same thing as, yeah, it's a y tilde is predicted by the model.
So then they take y tilde and then they try to go backwards
Yes.
and see if because you said you can go from x to x tilde. Now you want to go from x tilde to y tilde to y. Is that correct? Or am I?
Yes, yeah, y tilde to y again, yes. So it's a Markov chain from y to x tilde to y tilde and then again to y.
And so now you have two parts of the problem. One is going from x to x tilde to, you're trying to fit y, but you're learning y tilde.
Yes.
I'm still
So
not quite sure.
one problem is we are trying to get x tilde and again y from the input data in one compression, and then if we have that y, we are trying to again get that y from the different root, which is like distributed differently, and it will have some kind of like it preserves, kind of trying to preserve the distribution patterns.
So in one case, you're saying my model is learning to predict y tilde, and now I have a distribution between x and y tilde, right?
Yes.
And the other is the distribution between x tilde and y. Did I get it right?
Yes. Yes.
And you're trying to force both these distributions to be as close to each other as possible.
Yes.
So one is based on the synthetic, what the model thinks is correct,
Mm-hmm.
about the output, and the other is based on what is actually correct about the output, but using the compressed version of X.
Yes.
Oh. It sounds like a sort of an error correction thing where you're learning to predict something, and then you're going back and using your prediction to see if it's consistent. I'm still struggling a bit, but there seems to be that quality in there. So if it learns noise for y tilde, then that will not be useful for prediction. And the second part is trying to ensure that it doesn't learn noise because the noise is not useful for prediction.
Yeah.
I'm trying to look through the paper to see if there is any clarity, and not really.
It sounds a little like expectation maximization to me, Praveen.
Yeah, that is true. I mean, they acknowledge something similar in there. Basically, they're saying that the left-hand part is essentially the labeled prediction, and the right-hand side is the unlabeled prediction.
There's something in the deep learning book by Benju et al. Where they talk about something called elbow, expected lower bound optimization, which has similar qualities to expectation maximization. So this sounds like something that's worth digging into because it's an interesting concept.
So Tarun, I mean, you've said a few times, so these guys have not tested this on any data. I mean, they basically, or it's not well tested, it's a theoretical framework.
Yes.
Okay.
When you say not tested on any data, they did it on simple data, or they used it only on
very
synthetic
simple.
data?
Yes.
Real data or synthetic data?
Synthetic data.
Okay.
Actually, they used that very famous data set CFIR, or
Okay.
yeah, they used
The image data set.
Yeah.
image data set. Yeah.
So they did use some real data to try to train this for classification.
Yes. But very small, like probably part of that, not the entire data set.
Okay. Don't know about you guys, but I would like to stay with this topic for at least one more meeting. If you guys are okay with that, might be because there are a bunch of questions here that seem to need clarification.
So you're suggesting we dig into this paper a little bit more, or something else?
I'm suggesting we dig into this paper a little bit more, but if there's something relevant you want to, that would help, I don't have an objection to that.
I think it's worth digging it because I am also not very clear on that, this particular slide, which is showing training and prediction as the way it is depicting.
Mm-hmm. Yeah, I'm always confused when they reverse the path. It's going from y to x tilde to y. I guess that's meant to indicate a loop, because I always think of it as from x to y, or x to x tilde to y.
Actually, they put it y before because we already know we have access to the probability distribution between y and x, and they are trying to do mostly on the images. The images, we have the input information and what we want to get from that image. So that's how they are going from Y to X tilde and then looping back.
But is it that we want the distribution of X tilde Y tilde to be the same as the distribution of XY, or we want the distribution of X Y tilde to be the same as Y X tilde Y? That's the part that's confusing me. Or both.
I'm wondering if that training phase that they're depicting on the top right figure, Y X to X tilde, is actually the back propagation phase.
Yeah, that would make sense. Yeah.
Right. So you do the back propagation and you basically figure out your X tilde and then go from X to X tilde to Y.
That's your prediction phase. That makes sense.
Okay, yeah, it's worth digging in a little bit more. My only concern is I'm out. I'll be on a plane on the 6th, as is scheduled.
We can always change the date.
Yeah. So
should we move it up a little? Move it up a week to the 29th?
no, that week won't work for me at all.
Okay.
I can do on the 5th, but that is too close to the long weekend. So people might still be out in there. Or we can skip the 6th and then go to the 27th and do it there. I'm out 6th and 13th.
Out 6th and 13th. The next week would be the 20th.
Which is just 1 week before the 27th scheduled meeting.
I see. Okay. Well, unless we have somebody else lined up to present something else, we could just dig into this some more. But we should have a specific plan. Tarun, are you willing to dig in some more?
Is the code available, Tarun, for this at all?
I can try and email them to get the code if they had tried to CFIR.
If it's on archive, then usually they have a link, no?
Yeah.
Are these papers from archive or are they published?
They are from archives.
Okay. Would you do us a favor and or Leela or somebody and email out the links to these papers again, along with the link to your PowerPoint?
Yeah, sure. I will share.
Leela, what was the other topic that had been proposed?
Leila, are you there?
Yes, I'm here. Can you hear me well?
Yes.
Oh, yeah.
Okay. I think this paper was part of a thesis. And in that thesis, there is a collection of 3 papers. So we were thinking on discussing those 3 papers first.
And this is just one so far?
Yes.
What are the other 2?
I can quickly look at them. I think that
we discussed about last time we were discussing about this dual information bottleneck and representation compression and generalization in deep neural networks.
Yes.
That's the one you covered now, or that we did not cover?
So I covered dual information bottleneck, but representation compression, this one we didn't do till now.
Representation compression. Okay.
Yeah.
So maybe it'd be a good idea to bring that one up too. Are you ready to dig into that too, or do we need to find somebody else to cover it?
So I think maybe we should just next time dig into this a little bit more and then go on to the next one. Otherwise, we may not be able to cover enough in one meeting.
Okay, fair enough. But Leela, if you wouldn't mind sending all the links again, including the representation compression one,
Of course. Yes, I will send
because
all of them.
yeah, I will try to read that and see if that's relevant to our conversation. Yeah, at
Of
least
course.
about this part. Yeah. Actually, if you could, if you don't mind, could you send them my email?
Yes, absolutely. Yeah.
Yeah. Thank you.
Sure.
Yeah, personally, I think getting our hands around this concept is important because it is one of the key things linking information theory to machine learning.
Right. And what seems interesting in here is that they're basically making it tight knit in the sense if they're minimizing the cost function that is based on from information theory, then it is bringing machine learning and information theory very close rather than saying, okay, we're going to train the machine learning and see what information is being mapped, right? So this is a more deliberate effort to make sure that the two are coupled.
I rather suspect that one of the things that will happen, as has happened in other machine learning areas, is that if you can't compute a specific info theory metric explicitly, they will come up with alternative metrics, which are surrogate metrics, and then and use those for the training because those can actually be computed in a more accurate way. But then use these metrics as ways of tracking what's going on.
I have a suggestion though, Hoshin. Hold on, give me 1 second. So in our group, we have been looking into a parallel reading effort on some of these papers, and I think Aramidi was talking about some things going on at Microsoft Research where they're looking into causal behavior. And I'm going to share my screen just for a moment in here. So Aramidi, are you there? So this is what you sent me. Okay, so they're looking into deep end-to-end causal inference. So this is, they call it DECI. And this is a conceptual diagram for what they're trying to do. I hope you can all see this.
Could you make it just a little bigger? Sorry, my screen is only a 13-inch.
Yeah, I'm going to make it bigger. So is this better?
Much better.
Okay, so imagine that you have this series of variables, 5 variables and values associated with that, like the time series, right? So vertical is in the time in there. And when we think about causal inference, we essentially try and learn this causal relationship. In what we are doing is essentially directed acyclic graph, right? And we can infer what these dependencies are, in our case, causal dependencies, but then we cannot use these directed acyclic graph to make predictions. And so we have to then figure out a way to rely on machine learning to do that. But then these get decoupled, right? So machine learning does one thing. So what they are trying to do is combine these two into a single framework. And so they call it DECI. So this is, where is this? Yeah, deep end-to-end causal inference. So this is where it is. And the idea here is to do the kind of thing that essentially what Tarun was talking about, but now over a directed acyclic graph and not these Markovian layers as in the convolution neural networks. So the idea would be that you take advantage of the structure of dependency and then use the same structure of dependency to make predictions. Okay, that's how I understood it. I haven't finished reading this paper in there.
What do you see as the difference between the directed graph and the network structure? I guess I'm not seeing.
So the directed graph can loop back several time steps.
Ah, okay.
Okay, so it's not one layer feeding it. So it's not a Markovian layer, but essentially you have a causal structure. So a variable, say x1, could be influencing a variable x5, 5 steps or times 7 time steps later. So
Okay.
this goes again. So this is moving away from an image kind of a problem into a dynamical system kind of a problem where you have memory in time. And so I'm wondering, based on the conversation today, whether some of that information bottleneck ideas could be brought into this framework and help us with prediction in time.
Do you see any difference between what you're saying and an LSTM?
So I'm imagining that this is a deliberate incorporation of a causal structure rather than LSTM just arbitrarily inferring what that might be. LSTM essentially relies on these activation functions, which are rather arbitrary, and then a whole bunch of different number of hidden layers to figure out a composition of this activation function, which then mimics potentially a causal behavior, but has not been explicitly incorporated. So if we could bring those two to bear on this, I think there might be a value to thinking about this in there. So if you wanted to add another paper, I'm going to suggest that.
Could you send me that one too, please?
I'm going to put it in this chat here so you can download directly.
Okay, I got it too, and I will share it with everyone too.
Perfect.
So, Aramidi, can I volunteer you to maybe talk about this paper, or maybe you can work jointly with Tarun for the 27th?
27th of June?
July.
July. Yeah, that sounds good.
So there's still time, month and a half. And
so we skip July 6th.
Yeah, maybe. I can't see a potential date for that unless we do it on July 5th.
Okay, I'll let you guys decide and let me know.
Yeah, I think July 5th may result in low attendance like today because of its people would be probably taking a day off, given that for Mondays off.
Sure.
So let's skip, and then that gives time to Tarun and Aramidi to work a little bit more together on this, dig a little deeper, and if you can find code or other things, implement. And let's think about how. I mean, I don't think I'm expecting anybody to solve the problem, but at least find possible linkages between the two ways of thinking about it.
Sure. Maybe we could, Leela, propose having the 27th meeting be a 2-hour meeting?
Yeah, it sounds good.
Okay.
You should change the calendar invite now.
Yeah. Okay, I'll do that.
Yeah, no, this sounds very exciting.
So, I mean, basically, this dual bottleneck idea starts to couple machine learning with neural network. And then the other one starts to couple directed acyclic graph with neural network or deep learning,
And the
perhaps
stuff,
there
yeah,
is something there.
the stuff that Yuan and I are doing is trying to reproduce physical state space model structures using machine learning. So it has the same quality of building a causal loop, but using Markovian memory, so that we're not learning some kind of abstract thing, but learning something that's actually supposedly causal anyway.
Right.
If I understand correct the way you're talking about it. Yeah.
Okay, this will give us a little bit time to dig into this thing.
Perfect.
Okay. Anything
All
else?
right. Just let people know. We've had some conversation by email. I'm not sure how much people are in the loop, but we're thinking about organizing the next IT workshop in 2023 in Europe. Right now is the proposal, possibly in September timeframe. But I know it's early days, but just keeping you guys in the loop on some of the conversations that have been happening.
I mean, that's a very exciting place, and I think which month were we there? We were in April over there, right?
We were there right after EGU. We all went to EGU and then went by train or whatever.
Right, yeah. So we were coming out of a winter, so it was still very cold and beautiful there. I don't know, September, whether it's going to be just as snowy over there or not.
I mean, one possibility is still to do it around the context of EGU. We had suggested that as one possibility, and I said that's fine. It just means I have to make 2 trips that year. So he was trying to consolidate it to one thing, but obviously we'll go with whatever the majority. It's better for the majority. So.
And the restriction is 30 people.
Right. So it'll be more focused. And as we proposed, it's along the lines of what we've been discussing here, trying to bridge machine learning and information theory, trying to understand that relationship better. So we need to think about who might be some invited, potential invited speakers. Okay, guys.
Okay, thank you. Thanks, Tarun.
Thanks, Tarun. Thanks, Leela. Bye.
Bye.